Oh, hi. I didn't see you there. No, just kidding. Um, this is actually a really good book, The End of Everything by Katie Mack. She's awesome. It's about the end of the universe. And I just got to the part where she starts talking about entropy and all this stuff and how entropy is kind of how we define time and all this other stuff. So, really interesting. If you want to do some more reading about entropy, this won't have any bearing on the class or anything because it's all astrophysics instead of chemistry. But I know you guys have all kinds of free time, so I figured might as well make some book recommendations. But it's an awesome book. You should definitely check it out. I really enjoyed it. Um, what I want to talk to you today about, or in this video, is equilibrium. And so when we have a reactions, how do we know when a reaction is complete, right? When does a reaction stop making more products, and how do we know that? And so we're going to delve into that a little bit today. And the nice thing is that this is, I think, the math on equilibrium constants, and equilibrium ends up being a little bit easier than the kind of uh, a whole bunch of algebra that we've had to do in a lot of the reaction rate stuff. So the math here gets a little bit easier. Conceptually, I think it's one of those things that takes a little bit of time to get used to. So it's better to just kind of get started now so we can put in that time and get to the point where it all makes total sense. All right, here we go. All right. So reactions, the first thing that we need to say is that reactions do not proceed in one direction only. Right? So we've been thinking about this as if we have reactants on one side, and then there's an arrow, and we go to products. Right? So reactants to products, this is the way that we think about chemical reactions, but in reality, there's also another arrow where the products are actually reverting back to the reactants. Right? And this is a fundamental property of chemistry. In every reaction, there's always a way for the products to become the reactants again. They might not do it very quickly, but it can always happen, right? Because if we can make a bond one direction, we can break that bond going the other direction, right? Now, if we have a rate of our reaction going this direction, it stands to reason that we'd have another rate of the opposite reaction, right? So we have a rate of reaction for reactants going to products. We have a rate of reaction for products going to reactants. And because the rates change with concentration, right, as time goes on, our concentration of our reactants decreases and our rate slows down. The concentration of the products increases. So that means that this opposite, this inverse rate right here is going to increase because we have more of our product in there. And eventually, at some point, these two rates will be equal. These two rates are equal. That point is called equilibrium. Because think about what that means for those two rates to be equal. That means as fast as we are creating products, we're also creating reactants. And so even though the reaction hasn't stopped, there's still a reaction rate going in both directions. Overall, the concentration of reactants and the concentration of products ends up being constant. Because for every reaction or every reactant that creates product, you have a product creating an equal amount of reactants, right? Because the rates are equal. Right? So at equilibrium, concentrations no longer change. Okay? Let's look at an example. Let's take N2O4 and watch it decompose to 2 molecules of NO2. So in this reaction, there's a rate of reaction going this direction. And if we figure out the rate, or sorry, there's a rate of reaction going in the forward. I'm just going to erase this for now. There's a rate of reaction going in the forward direction. And if we figure out the rate law for this, we get that the rate equals whatever the rate constant is times the concentration of N2O4, right? So the rate depends on how much N2O4 is around. Once that's around, that tells us how much NO2 we get. But let's talk about the reverse reaction, right? What if we start with NO2 and go to N2O4? We can figure out the rate law for that too. And the rate law in this case is a second order reaction in NO2. Okay? So if we look at a reaction where N2O4 and we have rates going both directions, we set these rates equal to each other, right? So if the rate of reactions of each of these is equal to each other, K, we can say K times the concentration of N2O4 equals the K, we'll call this K2 because we need to differentiate these two, times the concentration of NO2 squared. We can solve this and put all the concentrations on one side and all the Ks on the other side. And what we'll get is, we will get, what do we get? We get K2 over K1 equals, no, this is the wrong way. I don't want to do it that way. All right, changing my mind. K1 over K2 equals the concentration of NO2 squared over the concentration of N2O4. Right? So I divided both sides by the concentration of N2O4. I divided both sides by K2. We're going to combine these into one term and call this KEQ. So this is a capital K now. We've been drawing lowercase k's this whole time for reaction rates. KEQ is our equilibrium constant, because this is the rates at equilibrium, right? This is the ratio of the rates at equilibrium. This is KEQ. And then the concentrations, right? Notice that this is the concentration of the product in NO2 over the reactant in N2O4. So KEQ is our new constant. This is the thing we're going to be focused on for this entire chapter. KEQ is an equilibrium constant. And we have some rules about equilibrium here. So the KEQ is our equilibrium constant. And what it describes is it describes the concentrations of product and reactant, concentrations of products and reactants at equilibrium. KEQ is always in the form of the concentration of the products to some power, M, over the concentration of the reactants to some power, which we'll call N. The exponents here come from the stoichiometry. Exponents come from stoichiometry of a balanced equation. I see you twitching. We're not going to be balancing many equations in this chapter. We will get to balance some equations later, but for now, most of the equations you're going to get are going to already be balanced. Okay. All right, so the ratio of the rate laws gives us these types of things. So for example, let's say that we have, where did I go? I'm going to give you a different one, still using NO for some reason. 2 molecules of nitrous oxide plus Br2 is in equilibrium with 2 moles of NOBr. Okay. If we want to write an equilibrium constant for this reaction, we take the products, there's only one product, NOBr2, or NOBr, excuse me, and the stoichiometric coefficient is 2, so we make that our exponent. So on the top of our ratio, our equilibrium constant ratio, we have the concentration of products raised to the stoichiometric factor, which is 2. On the bottom, we have our reactants. So we have Br2, concentration of Br2, which doesn't have an exponent because the stoichiometric factor is 1, right? So our exponent is 1. And then we multiply that by the concentration of nitrous oxide, which is squared, because again, the stoichiometric factor is 2, right? So we're just going to take if you have more than one product or more than one reactant, you just multiply them all in there. Products go on the top, reactants go on the bottom. The exponents are the stoichiometric coefficients. that's equilibrium constants. So obviously there's going to be a lot more that we're going to do with those, but that's basically, if you get a reaction, you can now write the expression for an equilibrium constant. So stick around for the next one. We'll talk about how we use stoichiometric, how we use equilibrium constants and what kinds of manipulations we can do with them. So we'll do some math with these. I know you're excited. All right, see you there. Thanks.